This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
So welcome back to the W.E. Heraeus International Winter School on Gravity and Light. So tutorial 8 will be about parallel transport and curvature. As usually, we start with exercise 1 and some multiple choice questions. There is designed to spark discussion and as a self-test. So, is it correct that a parallel vector field is certainly a parallelly transported vector field? No, this is not correct. A parallel vector field is a weaker notion than a parallelly transported vector field. However, the inverse, that a parallelly transported vector field is certainly a parallel vector field, this would be correct. But in the way it is presented here, it is not correct. On a flat manifold, the autoparallel equation for a curve gamma in any chart, Ux is gamma double dot I of lambda is 0. So again, recall, in a flat manifold we have no curvature. Also, we have a collection of charts in which the connection coefficient functions all vanish. However, this doesn't have to be the case in every chart of the atlas. We already saw an example for the flat manifold, namely the flat plane, and an example for a chart, the polar coordinate chart, where the gammas didn't vanish. So, and then the autoparallel equation doesn't read only gamma double dot I is 0. So this is wrong. Newton's second law, formulated as Fi of gamma of lambda, is m gamma double dot of I of lambda, cannot be correct. Yes, this is now correct. So the statement is correct, as the left-hand side is a vector. The right-hand side, however, isn't. So this gamma double dot doesn't transform like a tensor. It is not a tensor. It is not a vector. Only if we would add plus gamma I mn gamma dot m gamma dot n. So the full autoparallel equation. So the full entry from the autoparallel equation, then the right-hand side would also transform like a vector, and then we would have Newton's second law. So, but in this form as is presented here, Newton's second law cannot be correct. On a flat manifold, parallel transport around a closed curve results in the same vector. Well, definitely it does. So if everything's flat, we have no curvature at all. If we take a vector and do parallel transport around a closed curve, we always have to end up at the same vector again. There's no chance to get any other vector. And the introduction of torsion does not change the autoparallel equation. Well, that is also correct. So, look at the autoparallel equation in the chart. We have that this is gamma double dot I plus gamma a I m n gamma dot m gamma dot n, of course everything with respect to the x chart, is 0. This expression now is symmetric under the exchange of m and n here. So here we only see the symmetric part of gamma mn, and the introduction of torsion would mean that we get an antisymmetric part into the gammas. However, the autoparallel equation only sees the symmetric part and doesn't take care about the antisymmetric one. So the introduction of torsion changes nothing. So the statement is correct. And the Riemann, so second exercise on here deals with Riemann curvature. Riemann curvature is not a 3-1 tensor field, it's a 1-3 tensor field. So the statement is wrong. It is antisymmetric in its last two slots. Well, let's therefore write down what how R is defined. Or, as we denoted in the lecture, it is Riem. It eats a covector omega and three vector fields z, x, and y, and is defined as the covector omega acting on covariant derivative with respect to x, covariant derivative with respect to y on z, minus covariant derivative with respect to y, and 1, 2 with respect to x acting on z, and we get minus covariant derivative of the commutator x with y acting on z. So now we can look what happens if we exchange x and y. So we exchange the entries in the last two slots, where we find that this is omega y, omega and nabla y, nabla x on z, minus nabla x, nabla y on z, minus, and here we change the order in the commutator. Also, if we change the entries in the commutator, we get out a minus sign. And then we see that we can pull out an overall minus sign, and we end up again at an expression we identify as minus Riem of omega x, y, sorry, no, this here is z, x, y. So if we exchange the entries in the last two slots, we pick up a minus sign. So, and this is the criterion for antisymmetry, so the statement is correct. The Riemann curvature quantifies the failure of second covariant derivatives to satisfy a Schwarz rule. Well, yes, it does. This was already shown in the lecture. The Riemann curvature has d to the power 3 times d minus 1 over 1/2 independent components. So, we therefore have to look at the component, so the representation in the chart. So we know that the Riemann curvature is a 1-3 tensor field. So it has indices A up and B, C, D down. And now we already showed in the second question that it is antisymmetric in these two indices, in these two slots. And in dimension, so maybe this D here is a little misleading, as this is also what we call dimension here. So let's just name it M. And we know that 2, so that if we have such an antisymmetric pair, we have D times D minus 1 over 2 independent components, just for this pair here. And we have two other indices left, A and B, that can run arbitrarily from 1 to D. So we have d possibilities in this slot, d times d possibilities here, and d times d minus 1 over 2 independent components here, which is just d to the power of 3 d minus 1 divided by 2 independent components of the Riemann curvature. So this is correct. And the Riemann curvature, if it is non-vanishing, obstructs the existence of coordinates with respect to which the gammas vanish. Yes, this is true. As we will see in a second, the Riemann curvature is fully determined by the connection coefficient functions, and thus if the curvature doesn't vanish, this means that the gammas cannot vanish everywhere. So this is correct. So we now have exercise 1 done, and we move on to exercise 2. So, where connection coefficients appear. So let's recall the autoparallel equation for a curve gamma in the chart free formulation as well as in the formulation with respect to a chart. So the chart free formulation is just that the covariant derivative with respect to some v gamma acting on itself, v gamma, is 0. And in the chart ux, we see that this is gamma double dot with respect to the x chart, and we take the ith component plus the connection coefficient function with respect to the chart x of indices I, m, n, and gamma dot m and gamma dot n is 0. So this is the autoparallel equation for a curve gamma. Both should be memorized. Next question is to determine the coefficients of the Riemann tensor with respect to a chart ux in terms of the connection coefficient function. So, we again write down Riem, the definition of Riemann curvature, which is Riem of omega x, y, z. That is omega of nabla x, nabla y on z minus nabla y, nabla x on z minus nabla of the commutator x, y acting on z. And now we use the chart-induced basis fields to find the components, so the coefficients of the Riemann tensor. So we say, we put omega is del xi. We use, so here we have to, of course this entry z goes here, the entry x and y are here by convention, so that everything is correct. So we use that z is the vector field del xj, x is del xk, and y is del xm. So we find that Riem of del xi, del xj, del xk, and del xm is so. We just plug in, we have del xi acting on nabla with respect to del xk. nabla del with respect to del x m acting on del x j minus nabla act on with respect to del x m nabla del x k acting on del x j minus nabla of del x k commutator with del x m acting on del x j. So we already got shown in the lecture that for such a chart-induced basis, this commutator is 0 and this term kicks out. So now we're left with these two terms in here. And now we identify this covariant derivative with respect to such a basis field acting on another one. Yeah, well, this was just the definition of the connection coefficient functions. So this is gamma r jm del x r. So what we get is, this is del xi on the outer covariant derivative stays for the moment, and the inner one gets replaced by gamma rjm del xr minus, and in this term the same happens, however we only have to exchange the index m and k. I will note it this way, since the exactly same things happen as in the left term, only exchanged with indices. So, and now we have here connection coefficient functions and this basis field, and we can act on it with this covariant derivative with the product rule. So, we find that this is del xi. So if we first act on this connection coefficient function, well, this is the action is then easy. We just take the vector field del xk applied to gamma rjm, and this is already everything, since this was a function. A covariant derivative acting on a function is just the vector field applied to the function, and now we find that, or we see that a covariant derivative with respect to such a basis field on a basis field, well, this is again a, and of course here we have this del xr, which has not been touched yet, and here we write the gamma rjm in front, and we have the covariant derivative with respect to del xk on del xr. Well, that gives us just another gamma with r and k as indices here, and del xs. We get the same terms again with the indices m and k exchanged here, and now we are able to pull in this del xi acting on these basis fields here. So we get that this is del xk acting on gamma rjm, and we get a delta ir, and in the second term we get that this is gamma rjm, gamma srk, and we get a delta is minus the same terms exchanged with m and k. And the result now is we have that this is del xk on gamma ijm. From here, from this other part, we get that this is minus del xm on gamma ijk, and this term here produces a gamma rjm, gamma irk, minus, from this part here, gamma rjk, gamma irm. And these are the components of Riemann curvature. Riem I, J, K, M. And this is an important formula which you need to remember. So we move on to the last questions of this exercise. First it says that we define the Ricci tensor, Ric, and is defined as the Riemann tensor with a contraction over the first and third index, and we fill in the two slots with two vector fields x and y, and does this definition define a 0-2 tensor? Well, yes, it does. The criterion for something to be a tensor is that it is multilinear, so the infinity multilinear in each slot. However, we don't need to check that explicitly in this case, as we know that the Ricci tensor is defined by the Riemann curvature tensor. So, and we know the Riemann curvature tensor is of course C infinity multilinear in each of its slots. We contract two of these slots, but of course in the remaining two slots it still is C infinity multilinear. So the Ricci tensor is a tensor because the Riemann tensor was one, and we define the Ricci tensor by the Riemann tensor. And the last question is now, does a one-dimensional manifold with a connection have curvature? Why? So, curvature is, so if we want to make any statements about curvature, we need to look at the Riemann tensor. So on a one-dimensional manifold, the only connection coefficient functions that can exist are gamma 1, 1, 1. There are no others since we are one-dimensional. However, if we now go back to the components of the Riemann tensor here, we see that if we plug in gamma 1, 1 everywhere, that this just kills out. So each term cancels and we end up at Riem of 1, 1, 1, 1 is 0. So the Riemann curvature vanishes everywhere, and so the one-dimensional manifold cannot have curvature, even if we define a connection on it. So this exercise provided you with some very useful formula that you should remember. So now we come to exercise 3, the round sphere, where we want to explicitly calculate components of Riemann curvature for the round sphere. So we consider the round sphere and a chart where the only non-vanishing connection coefficients are given by gamma 1, 2, 2 and gamma 2, 1, 2, which is equal to gamma 2, 2, 1, so we live on a torsion-free connection. Now we want to calculate component functions for the Riemann curvature. So we start with component Riem 1, 2, 1, 2, which lives on x inverse of theta phi, so it lives on the manifold. And we use the formula from obtained in exercise 2 for the components of the Riemann curvature. So this is del by del x1 living on x inverse on theta phi, and this acts on gamma one, 2, 2. That also gets evaluated on theta and x inverse of theta and phi. We get minus del x1. Or again, on the manifold, no, del x2 of course. And we get that this is gamma 1, 2, 1. Also of x inverse of theta and phi. Then we get plus, again a gamma, the r has to stay for the moment. And we have 2, 2 here, evaluated at x inverse of theta and phi. And we get gamma, the r stays here, we got a 1 and a 1, also on x inverse of theta and phi. And we get a minus, the r has to stay for the moment. We get 2, 1 at x inverse of theta phi, and the gamma of 1 r 2 x inverse of theta and phi. So now we see gamma 1, 2, 1 is vanishing. So this term goes out. Also, gamma 1 r1 vanishes no matter what we insert for r. So this term is gone. And from here, the only contribution we will find is for r equals 2. As we then have gamma 2, 2, 1 and gamma 1, 2, 2, which are both non-vanishing. So we then have to evaluate what this del x1 acting on this component function is. Well, this is basically the derivative. So what we get is we have to derive this expression here with respect to the first entry. So this is minus cosine squared theta plus sine squared theta, and from here we get a minus gamma 2, 2, 1 is the cotangent theta, and gamma 1, 2, 2 is minus, that gets a plus here, sine theta, cosine theta. So we know that the cotangent of theta is defined as cosine theta by sine theta. And we can insert this. We see that the sine theta cancels and we get minus cosine squared theta plus sine squared theta plus cosine squared theta, which is sine squared theta. So the component 1, 2, 1, 2 of the Riemann curvature is sine squared theta. And the question asks us now to also calculate Riem of 1, 1, 1, 2, of course also evaluated at x inverse of theta and phi. So we have to play the same game again. So we again have that this is del x1 acting on gamma 1, 1, 2 at x inverse minus del x2 acting on gamma 1, 1, 1 at x inverse plus gamma, r has to stay for the moment. We have 1, 2 here. And we have the gamma 1, r 1 here, also at x inverse of theta and phi. And we get a minus. The r has to stay. We get 1, 1 here at x inverse. And gamma 1, r2 at x inverse of theta and phi. So we see gamma 1, 1, 2, well, that definitely vanishes, so this one is gone. Gamma 1, 1, 1 also vanishes, this term is gone. Here we again get a term gamma 1, r1, where we see this also vanishes independently of any r, so this term is gone since this is 0. And here we see we have a gamma with 2 1s here in the lower entries, lower indices. Well, that is also vanishing independently of r, so this term is also gone, and we find that this component of the Riemann curvature vanishes. So now we have seen an example for the explicit calculation of the components of Riemann curvature. So, of course, there are more component functions of the Riemann curvature. So, for example, already here, this is of course minus Riem of 1, 2, 2, 1, as we now have exchanged the last two indices. However, we know that the Riemann curvature is antisymmetric in these last two slots, so we pick up the minus sign here. Other components could be Riem of 2, 1, 1, 2, or Riem of 2, 2, 1, 2, and of course also if you exchange both the last two indices, but that one is minus Riem 2, 1, 2, 1, and this one is minus Riem 2, 2, 2, 1. So these are all the other remaining component functions, and thus we solve the exercise. So we now move on to the last exercise, exercise 4, about how not to define parallel transport. So Hänschen defines two vectors x at a point P and y at a point Q as parallel if all their components with respect to some chart Ux are equal. And now we wonder whether this notion of parallelity is well defined, since it is defined with respect to a chart, so we have to check. And indeed we will prove that this notion of parallelity is ill-defined. So we look at the vector x, the one that lived on P, but in another chart y. So we know that x is a vector, so it transforms, like picks up the del yi by del xj at the point P, and we get that this is xj in the x chart. Now we can apply Hänschen's definition of parallelity, and we find that this is del yi del xj, nothing changes here at the point P, but now we know that all components of x are the same as for y in this chart x, so we can just pull in y here, but then we have to go back to the other chart, y, and we get del x j by del y m at the point q, since the vector y lives in TQM, and we get that this is y m in the y chart again. So now we see we have two terms from the transformations. However, the first one is evaluated at the point P, the second one at the point Q. So those two can't be contracted to a delta in general. So this is not the delta, and that's why, and so usually the components of this vector x in another chart are totally different from those of the other vector y. So this definition of parallelity is heavily chart dependent, and thus it is ill-defined. We now look at an example for this. So we take the real world R2, and we have a set of 8 vectors here. So in the real world, of course, we see, okay, they're parallel. So we know what R2 is, and we know that these vectors are all parallel. Also in the sense we defined it in the lecture. And now we go to the chart UX, which is just our Cartesian chart, so to say. And there we see, okay, these vectors are still parallel, and even parallel in the sense Hessian defined, so all the components are still the same. However, if we now look at R2 from our polar coordinate chart, this looks totally different. So we see that these parallel vectors, they get mapped to vectors that Hessian would never ever declare parallel. So the components of this vector here are definitely different from components of this vector. So even if in one chart the parallel vectors from the real world, as we say for parallel vectors, they also seem parallel in Hessian's definition. However, in the other chart here, they are not parallel for Hessian. However, for us, they are still parallel, since we know that this is only the chart representation of these vectors, but we have to decide for parallelity on the real world, so on the manifold itself, and there we know, and there we can see these vectors, these 8 vectors are parallel. So this is the end of this exercise, and since this was the last exercise, also the end of the tutorial, and we hope to see you next time.